Hello and welcome to today's lecture on MOS memories. Since the dawn of electronic era, memory devices have been found to be an integral part of electronic circuits and systems. You cannot think of any system without some memory. Particularly, the semiconductor memory has some kind of enabling, can be considered as enabling technology of the computer technology. That means, the computer technology has evolved based on the evolution of memory devices. So, without discussing about memory devices, our discussion on MOS circuits is not complete. So, today I shall try to give an overview of MOS memories. Obviously, it is a vast subject. You can get a complete book on MOS memories, but in a single class a single lecture I shall try to give an overview of MOS memory devices. And here is the outline of my lecture. Introduction, it will be followed by static RAM cell, how a RAM cell can be realized by using MOS transistors, then use of sense amplifier, then memory architecture, MOS memory architecture, then we shall focus on dynamic RAM cells, read only memories, and I shall conclude my lecture with some concluding remarks. How do you characterize a memory? It has been found that there are three important parameters which can be used to characterize a memory device: area, speed and power. Area is important from the viewpoint of its physical implementation by VLSI technology. Smaller the area per bit, you can accommodate more and more devices or more and more memory on a single chip. Obviously, if you can accommodate large number of devices on a single chip, cost per bit reduces. So, area plays a very important role, and with the sinking size of MOS memory devices, the number of memory devices that you can put on a single chip is increasing. For example, nowadays you can have 256 megabit chip, I mean that is dynamic RAM chip. Then speed is another important parameter, is speed. Speed of operation plays a very important role. The performance of electronic circuits is increasing. The computers and other systems are operating at higher and higher speed. So, unless the memory devices are available which can operate, which can communicate at that speed, you cannot really build a system using memory and those processors. So, speed of operation, which is usually specified in terms of access time. So, this access time has reduced from microsecond to nanosecond and less than nanosecond in the present days. So, speed of operation is another important parameter which specifies the performance of a memory device. Then finally, the power. Power is becoming increasingly important because MOS memories are used in many battery operated portable systems like cell phones, PDAs, MP3 player, camera and other things. Obviously, a memory constitutes a significant portion of that. For example, if you look at any present day processor, you will find that more than 50% of the real estate is occupied by memory. And obviously, power dissipation of memory will play an important role. That is the reason why power dissipation of the memory is important, and you have to develop memory devices that will consume lower power. Now, how do you classify memory devices? the classification can be done in various ways, particularly in 3 distinct ways. The first one is based on operation mode. Operation mode means whether you can perform only read or you can perform read and write. So, based on that you can do classification. There are memory devices which are read only, that means in the normal mode of operation you can only read from them. On the other hand, there are memory devices which are read write, that means you can perform read operation as well as you can write perform write operation in normal mode. So, based on this you can classify in 2 categories, read write and read only. Under the read write category you have got SRAM, static RAM, DRAM, dynamic RAM, EPROM, erasable programmable ROM, and then electrically erasable programmable ROM, EEPROM, and flash memory. These are all read write memory devices. On the other hand, mask programmable ROM, or there is another one which is not written here, fusible link ROM, these are read only. That can be that means they are programmed once, either at the time of manufacturing or user can do it using a special device known as PROM programmer, but that can be done only once. So, those are read only, and of course, the other types, for example, EPROM, EEROM, they can be pre-programmed. You can perform read and write, but later on we shall discuss how exactly writing can be done on them. There is another way you can classify is based on data storage mode. Data storage mode means based on that means how it is stored and how long it remains there. In this way you can categorize into 2 types, volatile and non-volatile. Volatile memory devices will actually it seems that I have written volatile memory devices will actually store information as long as power is there. As soon as power is turned off, information is lost. That means, volatile memory devices can retain power, as can retain information, can store information as long as power is there. On the other hand, the non-volatile category, which are read write type and read only type, can retain power even when power is shut down, power is turned off. And we can see SRAM, static RAM and dynamic RAM belong to the category of volatile memory, and non-volatile types are read write. In the read write category you have got flash memory, EPROM, EEPROM, and also mask programmable ROM. So, these are non-volatile memory devices. That means, if the power is turned off, information will not be lost. So, in a computer system or any other system, we will find there is need for both volatile and non-volatile memory. Both are required in a system. Certain information are kept permanently and certain information are stored as they are used during normal mode of operation. So, both are required in a system. Finally, final categorization is based on access method. There are 2 basic ways by which you can categorize. One is random. There are some memories which are random access. Random access means you can read from any part of the memory. So, you may have, for example, 16 kilobyte. You can read any byte and the access time is same. So, these are random access. On the other hand, you have got non-random access, for example, serial access memory or content addressable memory. SAM stands for serial access memory and CAM stands for content addressable memory. In these cases, the access is not random. For example, whenever you read data from floppy or tape, floppy disk or tape, it is inherently serial in nature. So, there you have to read in a sequential manner, that is why they are called non-random. In case of content addressable memory, actually the entire memory is searched, and wherever there is a match between the content between the key and the element which is being stored, that data is read. So, in such cases these are non-random in nature. So, this is how you can classify the memory devices. Now, let us focus on static RAM cell, which is one of the most important component of any computer and other electronic systems. A static RAM cell can be realized by using 6 transistors as it is shown here. Essentially, it is realized in the form of two inverters connected back to back, and there are two switches. You can say there are two switches. Of course, these are all realized by using electronic circuit by MOS transistors. So, you have got two inverters connected to back and two switches through which you can perform read and write operations. So, this is the basic building block generic circuit, and this is how it is being realized. So, you can see this is an inverter which is realized by using T1 and T3, and another inverter is realized by using T2 and T4, and the output of this inverter is connected to the input of this inverter, and output of this inverter is connected to input of the other inverter. So, they are connected back to back, and these two transistors T5 and T6, they are used for performing read and write operations. You see both the gate of both the transistors T5 and T6 is connected to a line known as word line. Later on we shall see the access is performed in terms of word and bit line. So, word line or it is coming from row line also you can say, whenever this is 1, this particular line is selected, these two transistors are on. Then you can access data from the information which is being stored. So, in normal mode, as long as power is there, these inverters connected back to back will be in one of the two states. That means, output of this inverter realized by using T2 and T4 will be 1, and on the other hand the output of the other inverter realized using T1 and T3 will be 0, or vice versa. Now, that you can read with the help of T5 and T6, and information will go to the bit line, and from the bit line it can be transferred to the outside world through some interface circuit, that I shall discuss little later. And as you can see, because of this configuration, this 6 transistor CMOS static RAM cell has got the following features: low power dissipation. Low power dissipation is arising because as you know, CMOS inverters are inherently low power, because there is no static power dissipation, and as a consequence when these inverters are realized by using CMOS, they consume lesser power, and also high switching speed is achieved by using this type of configuration. And as you know, there is good noise margin of CMOS inverters. As a result, static CMOS circuit, I mean CMOS RAM, static RAM realized by using CMOS inverters gives you good noise margin. However, because of the use of large number of transistors, 6 transistors per cell, that means to store 1 bit of information you will require 6 transistors, and obviously it will occupy large chip area. So, the large chip area is occupied by this by each cell, and as a consequence the number of memory cells or number of bits that you can accommodate on a chip cannot be many. So, static RAM cells, static RAM has lower smaller chip, I mean large chip area. So, number of devices, number of bits that can be accommodated is small. Okay. So, this is the basic structure of a static RAM cell. Now, let us have a look at how the reading and writing operation take place. Actually, in addition to a cell, I mean a cell in which the information is written bit, a particular bit, you will require additional circuit, particularly the sense amplifier and read write circuitry is required. Of course, these are common to a large part of the circuits. That means, the using the same sense amplifier you can read from a large number of memory bits. So, that means, this part is common and also this part is common. That means, apart from these apart from these 6 transistors, other transistors are common to other parts of the circuit. Now, how the reading and writing can take place? Let us explain how the writing occurs. Writing can take place by enabling these two lines, write bit WB and WB bit here, and proper value is applied to these lines, will come from outside. So, this will be applied here to the bit lines, and whenever, let us assume we want to write 1 in this particular bit. So, whenever you want to write 1 in this particular memory bit, what will happen? As you can see, 1 means this is your bit line C bar and bit line, this is bit line C. So, 1 will be available here. So, VDD will be available here and 0 will be available here. Now, whenever you want to perform read operations, this word line will be selected, and these 1 and 0 will be applied to these bit lines. That means, VDD some voltage close to VDD will be applied to this line and voltage close to 0 will be applied to this bit line. As a result, this row select line or word line is now selected. So, T5 and T6 are on. That means, whenever you are when this line is 1, what will happen? This will make this transistor T2 on, T2, this will make T2 on, because this will make T2 on because this is high. So, this will make T2 on, and this in turn will make, that means, the output will be 0 and this will make T3 on. So, as a consequence, this will be 1 will be written here, T3 on means this will be 1 and this is 0. So, this is how writing will take place. On the other hand, when this is 0, this 0 will turn this transistor off. So, this will is supporting, the one is supporting the other. So, you are applying both the signals and very quickly, because of regenerative feedback, very quickly the change occurs and you get 1 and 0 at the output of this inverter and the output of this inverter. Then these signals, word line signal is withdrawn, write signals are withdrawn, and information will remain in this cell as long as VDD is maintained. Now, how the read operation is performed? Read operation is little complicated, but I can explain that in simple terms. What is done? Read operation is preceded by a kind of pre-charging. Pre-charging is done with the help of these transistors, this transistor at the top. So, these two transistors are turned on and these bit lines are charged to more or less half the supply voltage, that means VDD by 2. So, they are charged to VDD by 2, pre-charged to VDD by 2. So, these transistors, these capacitors, which are essentially relatively large, will charge to VDD by 2. After that, for reading operation, performing read operations, this row select, the word line is activated, and when the word line is activated, what will happen? Depending on what is stored here on this particular in this particular cell, if this is 1, this 1 signal 1 will be connected to this line, that means charge will transfer from this point to this bit line, and if this is 0, charge will transfer from the bit line to this to this transistor T2. That means, there will be some kind of imbalance, here the voltage will rise and here the voltage will decrease. So, that is what will happen if 1 was stored in this particular capacitor, and that will actually influence, this is acting as a kind of differential amplifier. So, this cross coupled sense amplifier acts as differential amplifier, and when the clock is applied, what will happen, this will sense the difference, and accordingly it will do several functions like amplification, delay reduction. Normally the change at these bit lines is very slow because of large capacitances, because this is connected to a large number of devices, and this amplification is done with the help of this cross coupled sense amplifier. Small change of the order of millivolt can be sensed by this sense amplifier, and this will do the amplification. Not only it will do the amplification, it will do delay reductions, very quickly changeover will take place, and also power reduction occurs to for the changeover. As you know, if it is done quickly, the power dissipation in CMOS circuits is dependent on how quickly the output changes. As you know, if the output changes slowly, then there is a short circuit power dissipation, but if the change occurs quickly, then the short circuit power dissipation is reduced, and as a consequence this because of delay reduction, there will be reduction in power dissipation, and also it will restore the signal level to rail voltage. That means, the voltage level that you will get at these 2 points will be raised to VDD and ground. That means, normally because of charge sharing, what is happening here, charge sharing, pre-charge followed by charge sharing, and charge sharing is leading to increase of voltage at one bit line, and the complementary bit line is going in the other direction, and that is being sensed by the sense amplifier. It amplifies it, restores the voltage, and it does it quickly, and now you get rail to rail voltage 1 at the bit line and 0 at the bit line bar. On the other hand, if you write 0 in that part, if the bit is reading, I mean bit is the opposite, then of course on the bit lines the values will be opposite. Then the output is transferred. After sensing, this output will be transferred to the outside world through some sensing circuit. Now in this particular case, in case of SRAM, this sensing is non-destructive. That means, the information that is being stored here is not lost, because it is a flip flop kind of thing, and maybe the output will be connected, this output of this will be connected to the bit line, this output will be connected to the bit line. So, and current will be supplied by either by the PMOS transistors, and current will be synced by the NMOS pull down transistors, but information will not be lost. As a consequence, it is non-destructive, and as we shall see, not only in SROM, there are other type of dynamic RAMs where also this sensing is non-destructive. However, later on we shall see it is destructive in one transistor dynamic RAM, which I shall discuss little later. So, I shall not come to this topic once again, but that is why I am covering this. So, this part is different for different types of memory devices. This is for static RAM and other types of RAMs. This part will be different, but the sense amplifier and other parts will be same. Okay. So, with this discussion, now we can move to more I mean as we are following a bottom up approach. Now, let us consider chip level. It is not a single bit. Whenever it is packaged in a chip, you have got large number of bits. So, memories can be organized in the form of bits, bit organized, say 256 bit, or it can be organized in terms of words or bytes, say 4K into 8 bit. So, in this case we shall call it byte organized. So, irrespective of whether it is bit organized or byte organized, the reading, writing, operations, these are all same, except as you know, you will see that this reading operations, whenever it is of byte organized or word organized, you will see will perform reading simultaneously of one word. Anyway, here is an example. So, here a chip has been organized in the form of 2 to the power n into m. That means, m bit per word, and you have got 2 to the power 9 words, And how do you select a particular word? Word is selected with the help of address lines, and address is applied to the chip. This is a memory chip, address is applied to it, and along with some chip select signals. So, depending on whether you are performing read or write operations, for example, this is write enable, that means whenever you are performing write, then you will be 0, and chip select has to be applied when a particular chip is being used. And as you can see, you can read all the m bits simultaneously, and depending on these control signals, how various operations are performed is shown here. When chip select is high, irrespective of output enable and write enable signal, you will see the output is in high impedance state, high Z or high impedance state, and whenever chip select is selected and if both the lines are high, then of course output is disabled, again it is in high output high impedance state. On the other hand, when output is enabled and chip select is also enabled, both are low, then you can perform read operation and data will be read through these lines, through the interface circuit, data will be available on these output lines. Similarly, when write enable is enabled, irrespective of whether output enable is present or not, the data that you apply to it will be written into the memory cells, and internally this is the organization of the memory. So, you can see the address lines are divided, is partitioned. First of all, you can see these are the major components, memory cell array, which I have already discussed, memory matrix. Then you will require decoders, and you can see here there are two decoders, row decoder and column decoder. The reason for having two decoders is to reduce the complexity of the decoders. Instead of applying all the inputs to a single decoder, then the decoder complexity will be very high, but by using two dimensional selection of memory bit or memory word, that complexity of the decoders is reduced. So, they will require lesser chip area whenever it is organized in this manner. That is the reason why in all cases memory is organized in two dimensional form, two dimensional memory matrix, and you can see lower order bits are applied to the column decoder, on the other hand higher order bits are applied to the row decoder. So, in this case you have got 128 by 128 array, and of course, memory is little more 11 bits. So, 2 kilobyte. So, 2 kilobyte will require and it is organized in the form of 8 bits, that is the reason why it is organized in the form of 128 by 120 bit matrix. However, there are 8 bits per word. So, 8 values will be available simultaneously. So, you can see as you apply row address, row decoder is going to these lines, this row select line. So, as you know, the function of a decoder is to select only one of the 2 to the power n lines. Similarly, column lines will be selecting these lines, bit lines of a particular word. It may be 8 bit or 1 bit, depending on whether it is bit organized or byte organized. Then depending on whether you are performing read or write operation, the data will be written here. If you are performing read operation, then the data will be from the memory matrix will go to the to that sense amplifier. Then from the sense amplifier it will go to the interface circuit, and it will be available to the output line. On the other hand, if it is a read operation, data will go it will go to the through these lines, this input data control data will be written into these cells the way I have explained. So, this is how you can see you have got control circuitry, input data control, then column IO control circuit. I am not going into the details of these circuits, but you can understand from this basic block diagram how exactly they will operate. So, this is the overall structure of a memory chip. So, I have shown a RAM chip, it is not different in case of ROM chip, except there will be no reading facility, conventional reading facility. So, in a ROM chip. So, having discussed a static RAM chip, a cell, then the sense amplifier and writing mechanism, then a detail of a chip. Let us now focus on dynamic RAM. Historically, the dynamic RAM was proposed to reduce the number of transistors per cell. We have seen that in a static RAM the number of transistors is 6, and obviously it occupies large area. How the number of transistors can be reduced? First, what was done, the PMOS transistors were removed and the structure was somewhat like this. Now, you have got a 4 transistor cell. So, what is done, those PMOS transistors are no longer present here. So, this collector of this transistor is connected to the base of this transistor. So, here these are cross coupled, and these capacitors are not really external capacitors, these are all parasitic capacitors of the transistors. For example, this is the gate capacitance of T1, this one, and this is the gate capacitance of this one, and some parasitic capacitances. So, there is no explicit capacitors which are present in dynamic RAM cells. Now, these, as I mentioned here, in the quest for smaller chip area, 4 transistor dynamic RAM cells emerged. Now, as I mentioned, all RAMs are volatile, including dynamic RAM, static RAM as well as dynamic RAM. That means, if the power is withdrawn, information will be lost. But here there is one additional problem. Additional problem is, in case of dynamic RAMs, gradually the information is lost even when power is not turned off. That means, power is present here, but because of the leakage problem, these capacitors will leak. Any capacitor leaks. That means, information is what is stored there in the form of charge will be gradually discharged. So, the problem this problem can be overcome by periodic refreshing. What do you really mean by periodic refreshing? By periodic refreshing means, you will read the information, you will sense the information, then again write it. As you write it second time, again the voltage builds up on the capacitors. So, that means, refreshing involves reading and then writing back into the same memory cells. So, as you rewrite, again the voltage levels are boosted. So, this kind of periodic refreshing is necessary to retain information in the cells. And as you can see here, in case of dynamic in this 4 transistor dynamic RAM cell, although there is some reduction in the area, but unfortunately the area reduction is marginal. So, there is marginal area advantage over 6 transistor static RAM cells, and not only because of this, whenever you are going for dynamic RAM, you have to use you have to keep provision for periodic refreshing. So, you require additional hardware whenever it is a dynamic RAM, and as a consequence by shifting from 6 transistor static RAM to 4 transistor dynamic RAM, there is no significant reduction in area. So, this was not really very popular, but because of historical reason I have discussed it. Now, let us consider the second step, and second step was 3 transistor dynamic RAM cell. So, 3 transistor dynamic RAM cell were proposed, where one, it is instead of having 2 arms, 2 transistors, only one transistor is used, as you can see T2 for storing information. So, the gate capacitance of T2 is used to store information. Again, it is a parasitic capacitance, you are not adding any external capacitor there, and this is being used to store information. However, you will require 2 additional transistors T1 and T3 for the purpose of writing and reading. That means, whenever you have to write, this word line is selected, it is activated, these transistors turn on, and depending on the value on the bit line, this capacitor will be charged. That means, if 1 is present here, this will be charged to VDD minus VT. As you know, there will be a difference of VT, as it is charging through a NMOS transistor. That means, whenever it is charged to 1, I mean whenever you are writing 1, it will be this capacitor will charge to VDD minus VTN, where VTN is the threshold voltage of the NMOS transistor. On the other hand, whenever you are trying to write 0, then it will be 0 volt. This capacitor will discharge through T1, because bit line will be now held to 0 whenever you are writing. So, this capacitor will discharge through T1. So, this is how writing operation takes place. Writing operation takes place through this transistor T1 by selecting it with the help of this word line WL. Now, how do you perform read operation? To perform read operation, this transistor is turned off. However, the T3 transistor is turned on for the purpose of reading. So, for the purpose of reading, this transistor is turned on, and as you read it, as you turn it on, the state of this transistor is decided by the charge on this capacitor. That means, if 1 is stored in this capacitor, then this transistor will turn on, and as it is turned on, this will be discharged. That means, whenever you are when it is 1, then 0 will be written here, because this transistor is on and it will be discharged. So, the bit line here you will read 0 whenever 1 is written here. So, it has to be inverted to get the actual data. On the other hand, if it is 0, then this transistor is off, and this bit line will retain the value. As I mentioned earlier, the bit line is initially pre-charged. So, this remains in the pre-charged value, and because this T2 is now off, and there is it does not discharge through T3 and T2. This is how reading operation take place in 3 transistor CMOS circuits. Now, this 3 transistor CMOS circuits, I mean this dynamic RAM technology is quite popular because of 2 reasons. No additional capacitor is required for storage purpose, and the fabrication process is compatible with that of CMOS. Moreover, reading from a 3 transistor cell is non-destructive, as I have already told, and it is faster than 4 transistor cell. Because of these reasons, it is faster than 4 transistor cell. Reading the 3 transistor cell is non-destructive. No additional capacitor is required for storage purpose. The parasitic capacitor, the gate capacitance is of T2 is serving the purpose of storage device, and fabrication process is compatible with that of CMOS technology. That means, you can fabricate. So, suppose you are building an embedded system where you require some memory. So, this dynamic RAM cell can be fabricated on chip. So, this type of dynamic RAMs can be fabricated on chip, and in this case the reading is non-destructive. So, this is very advantageous, and that is why this is also used in many situations. However, in quest for further reduction in the chip area, 2 and 1 transistor dynamic RAM cells were proposed. So, 2 transistor dynamic RAM cell is essentially an extension of 4 transistor RAM cell, where the 4 transistor RAM cell we have already seen. So, those cross coupling is removed, and you have got so whenever you remove the cross coupling, those capacitors, those transistors are also removed. You have got only 2 transistors for reading and writing. Then question arises, where from do you get these storage capacitors? Unfortunately, in this case the information is not stored in parasitic capacitors. You have to fabricate explicitly these capacitors. How can you fabricate? As you already know, you can fabricate a MOS capacitor by using with the help of so you can on the substrate you can fabricate silicon dioxide, and top of that you can deposit polysilicon, that will form a MOS capacitor. So, just like the it is essentially the gate region portion. So, you can fabricate explicitly MOS capacitors and where you have to store information. So, these capacitors are essentially fabricated. So, as these capacitors are fabricated explicitly, there is no significant area advantage over 4T and 3T cells. So, this 2 transistor dynamic ramps were not very attractive because it does not did not give any area advantage, and that is the reason why these 2 transistor dynamic RAM cells were not very popular, and particularly very soon the 1 transistor dynamic RAM emerged. As you can see here, you have got only one transistor T1, and of course, you will require a storage capacitor that has to be explicitly fabricated, and this is the read write line, and this is the read write line, this is the bit line, this is the word line. So, you can see obviously, this will require very small chip area, and it has been found that it occupies roughly 1/4 of the chip area of that of static RAM, 6 transistor static RAM cell. So, it is very attractive. Now, to store 1, it is charged to VDD by VT. So, it is not different, and to store 0, it is discharged to 0 volt. So, writing operation is not very different from 3 transistor dynamic RAM cell. However, reading is quite different. So, whenever you do the reading, you can see this charge will be transferred directly to the bit line. So, this transistor is on. So, this charge will be transferred to this, and kind of charge sharing occurs, and this capacitor is not isolated from the bit line. So, what will happen? This is a kind of destructive operation. That means, the information that is being stored will be destroyed after you perform a read operation. Then what you have to do? After you have performed a read operation, you have to again write back the data, same data. So, to store you have to since read operation is destructive, you have to perform you have to restore the data by read operation is followed by restoration operation to restore the data, and also you will require sense amplifier for reading, as I have already explained. These are all required, sense amplifier is required in all cases. And as I mentioned, the chip area is very small in this particular case. It will occupy very small chip area because only one transistor and a MOS capacitor is required per cell. Unfortunately, process technology is not compatible with CMOS. That means, you cannot fabricate single transistor dynamic RAM on chip with a CMOS technology, with the help of the conventional CMOS technology. That means, the static RAMs chips has to be separate or off chip. You have to use separate chip for static dynamic 1 transistor dynamic RAM cells. However, the capacity can be very large. Nowadays, you can get a dynamic RAM chip occupying 256 bit or more on a single chip, and that has to be interfaced to the processor through some bus. So, this cannot be used for on chip applications, but for off chip this can be used. So, this is the dynamic RAM cell. Now, let us switch to another type of memory, that is read only memory. So, read only memory is a device that maintains a fixed relationship between a set of inputs and a set of outputs. So, despite its grandiose name, it is functionally very simple. If you look at the function of a ROM, read only memory, it has essentially got two components, a decoder and an encoder, as it is shown in this diagram. So, you have got a decoder, the function of a decoder is known. Whenever you apply some input, say there are n inputs, one of the 2 to the power 2n inputs will be active. Active means 1, remaining bits will be 0. So, that is the function of a decoder. One of the 2 to the power n lines will be 1. Now, In the encoding part, you can write some desired information. So, this relationship is usually committed to a physical structure either permanently or semi permanently. That means, you can store information in this encoder part that can be permanent. It will be done only once at the time of fabrication, that is known as mask programmable ROM, or there can be some fuses, those fuses can be blown only once, and so during the remaining lifetime of the device it will be used only for reading. And another very important property is ROMs are non volatile. That means, if you withdraw the power, the information is lost, I mean is not lost, information will be retained by this encoder in this encoder part. So, here is an example of a of what is how the information is stored here. Information is stored in a special type of MOS transistor. So, you have got a MOS transistor where information is stored. So, this side is ground, this is connected to the, this is coming from the decoder, and this is connected to the encoder line. Now, here what you can have a NOT type of configuration, this is connected to VDD. So, what will happen in this case, if this is 1, then this transistor will turn on, I mean this is not required. So, this will be grounded, and I mean this line will be grounded and you will get 0 here. On the other hand, these transistors may not be there, and when if 1 is there, obviously this will not be changed. So, you will get 1. That means, a MOS transistor is fabricated wherever the input will affect the output, and wherever it is not necessary, I mean 1 is to be stored, this MOS transistor is not fabricated. So, you can see here at this junction there is no MOS transistor. So, if this line is 1, you will get 1 on D2. On the other hand, that means, if the input is 0 0 0 0, then this top line will be activated and you will get 0 here on D1, you will get 1 here on D2, you will get 0 on D3 and 0 on D4. Similarly, if you apply 0 0 0 1, then the second line will be activated, and then you will get 1 0 1 0 1 0 at the output. So, it is acting as a kind of combinational circuit, and you can, and at the time of fabrication at these junctions, I mean between the encoder and decoder part, at these cross points, you can have a transistor or you may not have a transistor, depending on what you are writing, and this is permanent. So, this is the typical mask programmable ROM. So, at the time of fabrication, you will fabricate a MOS transistor or not fabricate, and this is actually known as NOR based encoder. You can have a NAND based encoder the other way. In that case, decoders will generate zeros, and in case of NAND based, the transistors will be in series, in a this is how a okay, let me draw several. Let us assume there are 4 lines. So, these are 0 active, and here you have got a PMOS transistor, and output is taken from here in a NAND based cell. That means, from the decoder the 4 lines will be 0 active, and you will have 4 NMOS transistors and a PMOS transistors at the which will be permanently on, and the output is taken from here. So, this is the typical NAND based ROM cell, where you are fabricating the encoder part is fabricated in the form of NAND rather than in the form of NOR as it is shown here. Okay. How do you realize erasable programmable ROM? erasable programmable ROM can be fabricated with the help of a what is known as FMOS or floating gate avalanche injection MOS. So, here a MOS transistor where you have got two gates, one is select gate, another is floating gate. So, you can see here the floating gate is between the substrate and the control gate. How it works? So, EPROMs combine the non-volatile property of mask programmable ROM and the read write property of RAM. So, you can perform writing also in this type of cells. So, basic structure is identical to that of the ROM I have shown. A special type of transistor known as FMOS is used in place of those transistors. The transistor has an adjustable threshold voltage that can be electrically charged. That means, whenever you have to I mean this floating gate, what can be done by using a technique known as electron injection process. If you apply a high voltage to the gate and also between the source and drain, the electrons will be attracted, will hot electrons are generated and that is being captured in that floating gate as it is shown here. So, floating gate in the electrons will go there and it will be trapped. So, electrons will be trapped in these regions, and as a consequence what will happen after the voltages are withdrawn, those electrons will remain trapped for years, maybe for 10 years. And then if you apply this standard gate voltage, this transistor will not turn on, because the threshold voltage is increased whenever electrons are trapped in these floating gates. So, essentially what you are doing, you are fabricating transistors of two types, one is of low threshold voltage, another is of high threshold voltage. High threshold voltage is above the the high threshold voltage is above the VDD. So, this programming is done using hot electron injection as I have already explained, but erasing is done by exposing to ultraviolet light. So, whenever there is a optical window in the erasable programmable ROMs through which you can expose it to ultraviolet light. So, these photons will transfer energy to those electrons and they will come out of these those that floating gate, and this is how erasing is done, and erasing takes place for all the transistors that is present in a ROM. Finally, EEPROM, they are the electrically erasable PROM, there the reading and writing operation is done by using a new technique known as Fowler-Nordheim tunneling. So, what is done here in this case, you can see the gate oxide thickness is very small, 10 nanometer. In the previous case, the gate oxide thickness was of the order of 100 nanometer, but in this case it is of the order of a small portion, you can see it is of the order of 10 nanometer. So, in this particular case, whenever a high voltage is applied on the floating gate, then electrons will tunnel through this region to the floating gate, and this is how the tunneling is done. And in this case, and writing and reading can be done by grounding either the gate voltage or the source voltage. That means, whenever gate is applied high voltage, electrons will tunnel to the floating gate, and if the source is grounded, the electrons will tunnel back to the source. So, this is how tunneling takes place in one direction or the other, and this can be used to implement electrically erasable programmable ROM. And both the programming can be done either by hot electron injection or by Fowler-Nordheim tunneling, but erasing is always done by using Fowler-Nordheim tunneling. So, with this let me conclude this lecture with some concluding remarks. So, I have given an brief overview of MOS memories. I have presented a brief overview. Now, MOS memories, as I told, are acting as kind of enabling technology of the present day computers. So, the present day computers are evolving with the evolution of MOS transistors. Then what is happening because of that? Many new products have emerged because of this evolution, for example, MP3 player, and some products have been pushed to oblivion like floppy disk, audio cassette player. Those are becoming obsolete, those are no longer present here, all are using MP3 player. and this is primarily because of this technology, this EEPROM or this is based on that, flash memory is based on this technology. And as I mentioned, cheap flash memory has replaced the audio cassette player and floppy disks, and cheaper flash memory will replace DVDs in near future, like MP3 players have already replaced the audio cassette players. So, this is not the question of if, but it is the question of when. So, time will come when again the DVD players will again go to oblivion, and you will be using those those MP3 like MP3 player, you will be having those flash memory based DVD players. So, those are coming in the future. So, with this happy note for future, let me end my lecture, and in the next lecture I shall discuss about sequential circuits. Thank you.